Hello, my lovely warriors. Welcome aboard. This is Shreyas here, your captain and your physics master teacher, and you're watching the big one-shot marathon session for Kinetic Theory of Gases. And this is specifically meant for 11th standard students. But if you're a 12th standard or a dropper student and you want to revise the topic, then you're most welcome. And what are we going to do today? Well, we are going to talk about mean free path, the ideal gas equation, problems on that, also root mean square, most probable speed, all of that, Maxwell speed distribution, and also we are going to see the pressure of an ideal gas and the kinetic theory of gas equation relating this RMS speed and pressure, and yes, degrees of freedom, law of equipartition of energy, and mixing of gases. All of this today, and I'm going live from my Bangalore studio. And in case you do not know me, this is Shreyas here, your captain for this channel. I am very good and I am negative, and that's the reason why I could be back to my studio. Till last week I was positive, but yes, somehow I was able to manage and take all the classes. But yes, now I'm negative. I'm so happy about it, and also I'm happy that I'm back to my studio, and yes, the big screen, of course. Welcome all my lovely warriors. Hi Roshni, Dakshin, EGL, Ankit, Ramya. Welcome Narbavi. Welcome Barni, Svetana, Kailash, Shiny. Welcome aboard all my lovely warriors. And how are your schools doing? Has it opened up? Are you still watching all the lectures online? And most of you who are watching the lectures online must be getting more time. That means you should definitely make use of the time that you're getting for your second term preparation. And in case you do not know, we have a lot of lectures on this channel, JEE Enthuse, which is an English medium channel. And we have covered so many topics. I have covered all the term 1 topics. I have covered, even the term 2 topics, so many of them. And right now we are on thermo. The only thing which will be left after thermodynamics will be waves. So stay tuned, make sure you have hit the subscribe button, and yes, those of you who had already liked the video, thank you so much. And yes, if you haven't liked it yet, please do that right away. Oh, Saja, your school is closed. I think you should be happy. Okay, Muhammad also school is closed. Thank you, Sunlight Forecast. Pongal vacation. Oh my God, Shiny, I never heard of Pongal vacation. I have heard of Dashara, I have heard of Diwali, Christmas vacation. Pongal vacation, really cool. Your school is good. I really like it. All right, so let's get going with the session. And before we go ahead, a big round of applause and congratulations to all the students who made us proud last year. 1,500 plus students cracked JEE Advanced from Vedantu alone. JEE Advanced, and this year it's going to be more, and you guys are next after that in JEE 2023. And yes, if you want to study in my batch, you want to clear all your backlogs, you want to revise the theory, you want more problems for practice, you want the test series, and you want a coaching in English medium, then go ahead, check out the link which is there in the description box below, because our classes are live plus recorded, and you are going to get the best teachers in the country at your doorstep without having to travel anywhere across. So go ahead, check it out, and you will see a lot of offers go on when you use my coupon code. Now, look at this, molecules, and look at the way they are moving. Their behavior is completely random. At least it seems so by the simulation. Now, many scientists and physicists, they try to analyze the motion of the molecules, and then they realize certain properties of the molecules, and they could relate it to the properties of the gases. Also, they made certain assumptions while studying their behavior, which are fair enough for ideal gases. And in JEE, especially in physics, you study mainly ideal gases. Yes, you can have real behavior, but we do not have too much of details about that, at least from the JEE perspective. So we are going to study the ideal behavior of the gases, but that is fair enough assumption for most of the behavior of the gases for decent amount of temperatures and pressures, which is okay. Now, when they analyzed the behavior of the gas molecules, they realized they could make certain assumptions via which you could actually talk about gas laws and so many other things which Otherwise would be very difficult. What are those assumptions? Let's see. First, all the molecules are identical, which is fair enough, and they are elastically going to collide with all the other objects. Meaning, when an object collides elastically, there is no kinetic energy loss. So when a molecule collides with a surface or with each other, there is no loss of energy, which is fair enough assumption. In reality, what happens when molecules collide? Then there are some electron transitions which happen and some photons are emitted, because of which there could be some energy losses. But let's just say that these photons are negligible in number, so there are no emissions which are happening. That means the collisions are elastic. That means the energy is conserved. Everybody with me? All right. Thank you. Oh, Nikhil, yes, the audio is awesome today. Yep, I have changed it to my collar mic. I've got it back. Yep. All right. Then the next thing, the size of the molecule is very small as compared to the empty space between them. Now, when I talk about the volume of a gas, then it should be the empty space plus the volume of the gas molecules. Now, usually we neglect the dimensions of the molecules because the molecules are very teeny-meeny. Even if they are plenty in number, the empty space is more than the size of the molecules, because of which it is a fair enough assumption, else we need to have some correction factor. But that's a good enough assumption when the volume is decently large and you have not pressurized the gas too much. So the size of the molecules is very small. Next thing, the molecules keep moving randomly in all the directions with all the speeds. Okay, here is a simple example. If I ask all the students of a classroom to behave in a mad manner, okay, just imagine you are in a classroom, you are a class of 100 students, and then I ask you to go crazy, to go berserk. There is no teacher in the classroom, but the doors are closed. And I ask you, you can do whatever you want, you can start running around like fools, like complete idiots. That's okay. You just have to act crazy. So you're going to run around. Each of you are going to have different speeds. You're going to collide with each other. Alright, you're going to be so happy about it. The same way, these molecules have energy, kinetic energy. They move around randomly. And there is no particular direction in which they go. It's like, when you move around in the classroom, you're not going to go in a particular direction. You're going to move in all the possible directions, equal probability. So the molecules of the gas, they have equal probability to move this way, that way, this way, towards you, away from you. All the directions are equal for the molecules. And they move randomly. That's what it is. Yep. So Shivali, don't worry, it's okay, you can chat, bacha, you can chat, but it's also good to interact, and yes, you can simultaneously also listen to whatever I'm saying. Is ideal gas hypothetical? Why are you studying it? When will we study real gas? Excellent question, Sajja. Even when I was a student, I used to always think about this. Sir, you are telling viscosity neglect karo, neglect friction, neglect this, neglect that. Sir, when are we going to study the real stuff? Please tell me that. Then I thought about something else. What if a second standard or a third standard student said, hey, these multiplication and additions and subtraction, this is just basic. The real stuff is integration. The real stuff is derivatives. So when am I going to learn the real stuff? Imagine a second or a third standard student sees those symbols of d by dx or integration. He is going to leave the school. He is going to drop out from school. He will be scared for life, right? Not just that, he will not even understand. So the same way you should understand, even in physics, chemistry, maths, bio, whatever you are learning, you have to learn step by step. You cannot directly jump over there because there are certain things which need to grow in a particular fashion. And that's why we study it step by step, right? All right, let's get moving. Hi Abhinav, hello Sidhu, I'm very good. Similarly, there are all possible velocities. This is very important. It's not that all molecules move with the same speed, they move with different velocities. The molecules keep colliding amongst themselves, also with the walls of the container. When they collide with the walls of the container, they impart some momentum. And when they collide, impart momentum, they will apply some force. And when they apply the force, it creates pressure. Yes, that's how pressure is created in the gas. Understand that. All right? Keep this in mind. And most important thing, there are no forces, be it attractive or repulsive, between the molecules. That's a very important assumption. There are no forces of interaction. You might have seen van der Waals forces in chemistry for gas laws. Those forces are negligible for ideal gases. You neglect it. Keep this in mind. But reality, you have gases which will apply forces on the molecules. All right. And this is another important thing, because the molecules move randomly and they move equally in all the directions. They distribute themselves everywhere. They will not accumulate at any point or place. They will be distributed evenly. So that's why the density is same throughout. It's not like all the molecules will go and accumulate over here. The density is same throughout. All right. Very good. Let's get going to the next one. Now that we have spoken about the assumptions in the kinetic theory of gases, let's talk about a very important quantity called as the mean free path. Now, what is this mean free path? Observe. Imagine you have a molecule. Okay, so this is nothing but a molecule. And what happens is this molecule goes from one point to the other. It is in motion. And then what happens is it collides with another molecule. The moment it collides, it might change its direction, speed, etc. It moves again until it collides again. And the same thing might continue. It might just keep colliding and it might just keep moving. Every time it collides, it has traveled certain distance before that. Let's say D1. After that, let's say D2. Then you have D3 and then so on and so forth. Every time it collides, before that it has traveled D1, D2, D3, D4 distances, right? Now, if I take, all right, just hold on, 1 second. Yep, 1 second guys. Yep. So if I take the average of them, so D1 plus D2 plus till the nth number, n is representing the number of straight line motions that the molecule underwent, divided by n, this will give me the average distance the molecule travels in a straight line path before colliding again. That average means mean, is called as the mean free path or the average path. So this is called as the mean free path. Usually the symbol is lambda. Some books use lambda with triangular brackets and all of that. So this is called as your mean or average distance between the collisions. So between the collisions, that's what it is. Now the calculation for that is more statistical. It's beyond the scope of JEE syllabus. It turns out to be root 1 by root pi into nd square. This is what you get. This is the mean average path between the successive collisions that you get. Now what are these numbers? Well, it's all written down right over here. And don't worry about this, I'll talk about it in a bit. Small n is the number of molecules per unit volume. That means, let me just put it up over here. This is number of molecules per unit volume. That means this is number of molecules upon the volume itself. Number of molecules upon the volume itself. D is the diameter of the molecules. This will be given to you in the question. It will be given to you. The size of the hydrogen molecule is this much. The size of nitrogen molecules is this much. They will give you that data. So 1 by root 2 pi nd square. This is what you get for the mean free path. If the diameter, if the molecules are heavy, big, then d square will become big. It's in the denominator. The mean free path will reduce. That means, the molecules will travel lesser distance before each collision. Keep this in mind. Everybody clear? All right, everybody clear? Excellent. Similarly, this number of molecules, if there are more molecules, if capital N is more, if there are more molecules, it is crowded, the free path that we'll be getting will also be less. That's why that N is there below. The number of molecules per unit volume. If more molecules are cramped, the molecules will have less space to travel between successive collisions. That's why the mean free path reduces. Last thing, how do you get this? This is also a very important relationship. Now that you get via gas laws. Simply put, think about it. Okay, this V is nothing but from PV is equal to nRT. All right, this V is nothing but nRT divided by P. So if you replace this volume with nRT by P, what are you going to get, my warriors? What are you going to get, my warriors? Think about it. You are going to get capital N divided by nRT, and P will come on the top. That's it. All right, so that's what you are going to get. But remember, this is in the numerator. This is in the denominator. Small n is in the denominator. So when you substitute it over here, lambda will be proportional to T by P. Lambda will be proportional to T by P. So this is very, very important relationship. How mean free path changes with temperature and pressure. No, EGL, if diameter is big, then imagine big molecules. Imagine fat people in a classroom. When they move around, they will collide. When they move around, they will collide because they are fat. If they are thin molecules, they can easily sneak in and they can avoid the collisions. That's why when diameter is big, the mean free path reduces. I hope this is clear. Yep. Suvida, I'll start thermodynamics after heat transfer. Yep. All right. So I hope this is clear. This N, you can write it as capital N by V. V is nothing but nRT by P. So P by T, you can see it, P by T is in the denominator. So T by P will come as it is for lambda, the mean free path. Very, very important. All right. So let's solve some questions based on this. All right. Okay. Oh my God. Sunday you have a mock test, Shashank. So I'm pretty sure you are going to enjoy this session. Guys, lots of concepts, problems, concepts. The lecture is full of problems and concepts. All right. How many collisions per second does each molecule of a gas make when average speed is this much and the mean free path is 2.5 into 10 to the power minus 7? Okay. Anisha, the thing is, I could have taken kinetic theory of gases, in 2 classes. I would have taken one hour class. Effective class length becomes 50 minutes. Okay, so instead of doing 2 classes separately, I have decided I will do it in 1 class but for longer duration so that you can watch it in one go. Number 1, there is no reduction whatsoever. It is just like your nurture series. Okay, so this is nurture series continued for 11th standard. All right, let's see how many of you can get this question. Very interesting. What do you think is the number of collisions that are happening per second? So first of all, okay, here is the average speed of the molecules. That means from one collision to the next collision. Okay, so this is the first collision to the next collision. So this is the collision to the next collision. This is what I can write. The average speed. What's the average speed? It is 500 meters per second. All right, and the mean free path, the average path length is 2.5 into 10 to the power minus 7 meter. The question is, how many collisions are happening per second does each molecule of the gas make when this and this? So all you need to do is find how much is the time interval. Time is distance. Time is distance divided by speed, right? Time is distance divided by speed. And the number of collisions per unit time, it's like frequency. And what is frequency, my warriors? Frequency is 1 by delta T. Frequency is 1 by delta T. That means it will be reverse of that. So it will be nothing but the speed divided by the distance. Speed divided by the distance. That means all you need to do is put the value of speed, which is 500 divided by 2.5 into 10 to the power minus 7. So you can write this as 5 divided by 2.5 into 10 to the power 2, the 2 zeros, and 10 to the power minus 7 on the top will become 10 to the power 7. 5 divided by 2.5 is 2, and this will become 10 to the power 9. So this is per second. So these many collisions are happening per second. By the way, this is 2 billion. Okay, this is nothing but 2 billion collisions. 2 billion, you understand? Billion, this is what it is. Yep. Okay, yes, lambda is inversely proportional to pressure, correct, Ramya? That's right. Shashank, SHM is over long time back. It's there in the playlist. Don't worry, I'll update the playlist in case it is not updated, but SHM is already done. Okay, so many classes were done. All right, let's move ahead with the next one. Okay, so okay, so let's see what do we have next. All right, moving on. Yes, 2 into 10 to the power 9 per second. Gas loss, very important. Yes, this is nurture series continued. Yep, it is nurture series continued, but we are going to cover the remaining chapters a little bit quickly, because if I dissect the chapter into small parts, it will take a long time. I want to make sure we start with the revision of 11th standard also soon. So I hope you guys are okay with me conducting, instead of 3 classes, I will do it in 2 classes, so that way we will cover the syllabus faster. All right, now gas laws, very simply put, quick revision, whatever you have studied back in chemistry. Boyle's law. Boyle's law is when the temperature is constant. So when temperature is constant, what do you see? Look at this over here. So when temperature is constant, what do you see? Pressure is inversely proportional to volume. That's your Boyle's law. Charles' law, what do you see over here? You can see the pressure is constant. When the pressure is constant, then the volume is directly proportional to the temperature. This is your Charles' law. And then Lusac's law. What is that? That's when your volume is constant. When the volume is constant, then the pressure is proportional to the temperature. Combining all of them together, you get your gas law equation, which is PV is equal to nRT. The value of R in SI units is 8.3. This is SI units, if you use SI units. Okay, but if you use liter ATM, then it will be 0.08. Okay, but that is in liter ATM per mole. Some of you might be using that in chemistry and you might remember that. All right, great. So that is in liter ATM. All right, liter ATM, and you can see mole will come below and Kelvin will also come below. So per Kelvin per mole, that's in liter ATM. All right, so Charles' law is basically where you keep the pressure constant. If you keep the gas's pressure constant, if you heat the gas, the volume will expand. Pressure has to be maintained. That means the force which is exerted on the walls of the container should be same per unit area. So then if you heat it, that means temperature is increasing, you need to make it bigger and bigger, because there will be more energy. That's why temperature will be basically proportional to the volume. Yep, if you want to add more numbers over here, it will be 0.0821. Yes, you can put that. Great. This N is your number of moles. And remember, number of moles can also be written down as capital N by NA. This is your Avogadro's number, which is 6, approximately 6.02 into 10 to the power 23. This N stands for number of molecules. Keep this in mind. As simple as that. Alright, this is very simple. Let's start doing some questions on this. It will be interesting. Yep, there we go. Now, find the approximate, guess the approximate number of molecules in a vessel whose volume is 7 liters at 0 degrees centigrade and the pressure is 1.3 into 10 to the power 5 Pascal. Let's see how many of you can do this. Okay, come on, let's see how many of you can do this. Interesting question. Find the number of molecules. Let's see what do we actually need to do. First of all, okay, going back, we need to find number of molecules. That means we need to find the number of moles. And if you want to find number of moles, I think we should make use of the gas law equation. So gas law equation is nothing but PV is equal to nRT. Alright, so N will be equal to PV divided by RT, but small n is number of molecules divided by Avogadro's number, so that will be equal to PV by RT. So therefore N will be equal to PV NA divided by RT. That's right, PV NA divided by RT. Now what do? Just substitute the values. So let's see, what do you get? N will be equal to pressure is 1.3 into 10 to the power 5 into volume. The volume is 7 liters. Be careful, convert those liters into meter cube. 1 liter is 10 to the power minus 3 meter cube. So this will be 7 into 10 to the power minus 3 meter cube. Keep this in mind. Na, Avogadro's number, so just put it as 6 into 10 to the power 23. The whole thing divided by R into T. R is in SI units, so 8.314 is the value of R. And temperature, don't put it as 0, you will get 0 marks, because 0 is in Celsius, put it in Kelvin, so it is 273. Okay, now how are you going to do the math out here? Let's see. If I can do something, I'll write it as 1.3 into 7 into 6 divided by 8.3 into 2.73. Okay, I have taken two decimals here. I will keep that in mind and I'll write everything in the powers of 10. Let's see, what do you get? 10 to the power 5, 10 to the power minus 3, that's going to be 10 to the power 2. So I'm just going to get 10 to the power 2 here, and here I'm going to get 10 to the power 23. All right, as it is. Because I shifted 2 decimals, I have to also put 10 to the power 2 here. Now that makes the problem simple. This 10 to the power 2 and this 10 to the power 2 goes. Now look at this. 7 into 6, that's 42 roughly. Okay, 42 into 1.3 will be slightly more than 42. It will be more than 42, right? So it is more than 42 divided by, okay, divided by 8.3 into 2.73. 2.73 is very close to 3 and 8.3 is more than 8. So let's balance it out. 8 3s are 24. So somewhere close to 24. Somewhere close to 24. Now 42 divided by 24, it's less than 2, but I know the numerator is much larger than 42. And this is close to 24. So somewhere near about 2. Somewhere near about 2. Where is that number? I think it should be option A. That's how I solve the question and I get the answer. Is that clear, my warriors, how we did this? Is that understood how the approximation was done? You have to think logically in the exam. You can't sit and multiply all these numbers. If you're going to sit 1.3 into 7 into 6 and 8.3 into 2.73, division, gone, bacha log. Okay, Saparna, let's wait for the announcement, but I have already given my predictions in the video. You can definitely check it out. When will the JEE exam be conducted? All right, moving on to the next one. Yes, option A is correct. Maxwell's speed distribution. Maxwell's speed distribution. Let's have a look. 1.3 is there, Vishaka, I agree, but 1.3 is too close. Where is 1.3? I think 1.3 is not there. 3, 6, 4.8. It's not there, 1.3. Yep. All right. Oh my God, Selva Kumar, you used it in your school and you got reduced marks. Well, I think school mein it will not work, but yes, in JEE competitive exams, do all these things. And when you learn with me, I'll teach you all these tricks when we solve questions. Maxwell speed distribution. For that, let me just show you an animation. Okay, look at this. This is a beautiful simulator and this is a chamber. I can note down the temperature. I can figure out the pressure. It also shows me a chart of basically how the speed is like. I can also heat or I can even cool it, whatever I want to do. And here I'm going to pump in some molecules. Look at these molecules. These molecules are getting pumped inside this particular chamber. Okay, let's just pump in some molecules. Interesting. Look at this, the way they collide, the way they interact, the way they collide with the thermometer. It's showing some pressure. It's also showing some reading of the temperature now. All right, look at this graph right over here. This graph tells you the distribution, meaning how many molecules have how much speed. Over here on the lower side, speed is less. The molecules which have that very little speed is this much in number. Then as you see the speed increases, the molecules which have that higher speed also increases. It peaks out. there is a maximum value. And after a point, there are very few molecules with very large velocity. You can see most of the molecules have typical speeds over here. Very few molecules have very high speeds, very few molecules have very low speeds, and most of the molecules are around certain particular speed. Everybody getting this? Everybody getting this? Now look at this. If I heat it, see what happens? Oh my God, look at that. The graph just shifted. If you couldn't see it, okay, I will cool it first. Look at this. I'm putting some ice. The speed is going to reduce. Look at the thermometer. The reading is going down. Temperature is going down. Okay, let's cool it. The molecules have become very little in energy. They have very little energy. Now, I'm just going to heat it. Look at the graph, the way it shifts. Look at the graph. It's going to shift now. It's going to shift towards the right side. It's going to shift towards the right side. Look at this. Because the molecules are going to have higher speeds. Oh my God, look at the energy. The graph has shifted. Did you just see that? Isn't it amazing? Look at the temperature. Oh my God, it's really hot. I can also remove this lid. I can let off some molecules and I can just close this as well. Okay, be happy, you're free. This is movie dialogue from Dilwale Dulhaniya Le Jayenge. Ja Simran ja, jeele apni zindagi. So this is something like that. Basically it says do whatever you want, to hell with you. All right, great. Now let's go back over here. This is exactly the graph given by Maxwell. It says most of the molecules have a certain speed. Very few molecules have very large or very little speed. And he also said that, you know, the velocities, all kinds of velocities are proportional to the root of the temperature. Remember, this temperature has to be in Kelvin, okay, not in Celsius. It is proportional to the root of temperature. That means at temperature is equal to 0 Kelvin, what is going to happen? The velocities are going to be 0. It is going to be 0. It's all going to be still, stand still, statue, stop, can't move, 0 Kelvin. As the temperature increases, the speeds increase. That's what it is. All right, great. So let's solve a question based on this on your screen right now. Yep, let's see. Vedantu is using depressed simile. Oh, is it? Is that a depressed simile? A smiley? Oh, I don't know that. It looks like a grin, like forced smile. I don't know. Is that how it is? All right. Now, an ideal gas is enclosed in a cylinder at a pressure of 2 atm and temperature of 300 Kelvin. The mean time between two successive collisions is 6 into 10 to the power minus 8 seconds. If the pressure is doubled, temperature is increased to 500, the mean time, the average time between the successive collisions will be. Let's see how many of you can get this. Let's see how many of you can get this. Okay, Shaitan saying C. Come on, my warriors, figure this out. What do you think should be the answer? Now, for solving this question, here is what we are going to do. Time is nothing but the time between the collisions is going to be nothing but the distance between the successive collisions, which is the mean free path, divided by the speed. So this will be the velocity of the molecules. Mean free path is directly proportional to the temperature and inversely proportional to the pressure. Directly proportional to temperature, inversely proportional to pressure. Velocity of any molecule I just mentioned, so constant, and into root of t. It's always proportional to root of t. Let's do the math. Constant will become a new constant. T and root t will cancel. You will have root of t over here and you will have pressure over here. Root of t on the top, pressure below. All right, makes sense? Okay, now let's see what should be the correct answer. Now, in the question, the temperature has increased, the pressure has changed. So the entire equation has boiled down to only temperature and pressure. Nothing else is there. Nothing else is there. Yep. Now observe this. Delta T2 divided by delta T1 will be equal to T2 by T1 will be equal to root of T2 by T1, and you will have P1 by P2 because it is inversely proportional to pressure, directly proportional to root of temperature. T2 by T1. What is the final temperature? 500. Initial temperature, that's 300, right? So it will be 500 divided by, initial temperature was 300, root of that, P1 by P2. The pressure is doubled. P2 is twice of P1, alright, and this delta T1 was 6 into 10 to the power minus 8. So therefore, delta T2 will be 6 goes on the top into 10 to the power minus 8 divided by 2 into root of 5 by 3. 6 by 2 is nothing but 3 into 10 to the power minus 8 into root of 5 by 3. Now observe the options and check it out which one will be correct. Which one will be correct? Think about it. Which one will be correct? So it will be more than 3. So 2 is not the correct answer. C won't be correct because it is 0.5. D also won't be correct. It will be more than 3. So option B should be correct because root 5 by 3 is more than 1. So 3 into a number more than 1 will be close to 4. Hence that should be the correct answer. Yes, it is. Yes, it is. Got it? Very good. All right. Let's get moving to the next one. Now, in the previous graph, I told you the molecules have different speeds and their speeds are proportional to the temperature. But we have 3 different kinds of speeds which are going to give you a general idea of that graph, that Maxwell's distribution. One is basically called as the root mean square. Second is called as the most probable speed. And the third one is called as the average or the mean speed. So average speed, root mean square, and the most probable. Just going back to the graph, I'll tell you what all of these are. Simply put, most probable velocity is what it says. What is the most likely speed of the molecule? And you can see there are many molecules with this particular velocity over here. So the highest point represents the most probable velocity, the most likely velocity. That's what most likely velocity or most probable velocity is. Average speed is just the average. Your height is 2, your height is 3, your height is 10, your height is this, your height is that. Average 2 plus 3 plus 10 plus 6 divided by the number. That is your average. Third is the root mean square. Root mean square is the root of the mean of the squares. Simply put, that means, look at this. If I have one molecule with certain speed, another molecule with some other speed, just square their speeds and take their average and then just take the root finally. What it looks like is something like this. Observe. If I have one molecule with speed V1, another molecule with speed V2, another molecule with speed V3, average will be just adding them and dividing it by 3. Root mean square means square their speeds and then obviously add them, take their average of the squares and then take the root of it. This will be the RMS velocity. This is called as the RMS velocity. That is mathematics. But what is the meaning of RMS? Why RMS? Why not something else? Why do we study RMS? Not many people know this. Understand, each molecule might have different velocities, right? V1, V2, V3, so on and so forth. So don't you agree? Each molecule will have different kinetic energies, K1, K2, K3, etc. Now, do you think that their average kinetic energy will be equal to half m average speed square? If I take the average of their speeds, V1 plus V2 plus V3 divided by 3, square it into half mv square, do you think that will give me kinetic energy average? Do you think we will get average kinetic energy? Think about it. Think. What do you think? Will it come out to be? The average kinetic energy? Okay. In the last question, it is increased. So no, Dakshin, it was fine. Yep. No, it won't be the same. Yes, it won't be the same. Yep. So basically, what happens is when you take the average speed, when you find the kinetic energy using the average speed, you are not going to get the average kinetic energy. No, this won't be equal. Nope, it won't be equal. Average speed is something else. Average speed, when you square it and multiply by half m, no, that's not going to give the average kinetic energy. But average kinetic energy will be obtained with some other velocity. Some other velocity, it is not the average speed. That speed turns out to be the RMS. So what is RMS? RMS speed is that speed which gives you the average kinetic energy of the molecule. Very, very important. What is RMS velocity? It is that speed which gives you the average kinetic energy of the molecule. That's why it is significant. Understood, my warriors? Yes, Aisha, thermal physics is almost done. This is the third lecture. We have done thermal expansion, we have done calorimetry, specific heat, and now we are on to KTG. Next lecture will be on heat transfer. So the RMS velocity by definition mathematically is v1 square plus v2 square plus v3 square plus v4 square, the average of that, the whole thing under the root, and it turns out to be root 3 RT by m. Very, very important. This is the formula which you are going to remember. Root 3 RT by m. This and this can be derived using these formulas. This and this can be derived using these formulas. I hope this is clear. I hope this is clear. Okay, so this is the formula that you're going to remember. Root 3 RT by m. You can again see the RMS velocity is directly proportional to root of temperature. Always root T will be there, no matter what you do. Okay, root T will be there. Okay, keep this in mind. Average speed, like I told you, it's just the simple average, the mean, the most average value, the average of all of them, the arithmetic mean. So V1 plus V2 plus V3 by the number of molecules. That value comes out to be 8 RT by pi m. 8 RT by pi m under the root. This is the value that you are going to remember. These values are not important, but I have given it to you. You can go from here to here or go from here to here by simple conversions. That K over there is Boltzmann constant. K is R by Na. Okay, so you can do the math and you can get that. It's not that difficult. Okay, so the point is 8 RT by pi m, the root of that will give you the average velocity and the most probable velocity. The molecules most in number with a particular speed will be given by the most probable velocity, and that will be root of 2 RT by m. Root of 2 RT by m. Keep this in mind. What is small m and big M? Very important. Yes, let me just put that over here. So what is this small m and big M? Capital M stands for the molecular weight. Molecular weight. Okay, so for example, for oxygen it will be 32 grams per mole. Correct? 32 grams per mole. But small m stands for the mass of a molecule. The mass of a molecule, and the mass of a molecule is molecular weight divided by the Avogadro number. So small m stands for mass of a molecule, capital M stands for the molecular weight. I think you would have used the same definition back in chemistry as well. I hope this is clear. Okay, I hope this is clear. Selva Kumar, how do they derive these things? Very interesting question. These equations are derived using statistical maths. Boltzmann gave a distribution curve equation which is in the form of exponent. So when you integrate and use the definitions of average and most probable, that's how you get it via integration. That is all statistical math. We do not study statistical math in relation with physics in J. So that's the reason why you don't have these derivations. Is that clear, my warriors? Okay. So finally, if I ask you which one is big, which one is less? Rho is density. Yes, rho is density. Correct. Rho is density. If I ask you which one is bigger among all these three, the RMS, the most probable and the average, then remember the most probable was root 2 RT by M. RMS was root 3 RT by m, and average was root 8 by pi. 8 by pi is almost 8 by 3. It will be between 2 and between 3. It will be between 2 and between 3. Hence, RMS, which has root 3, 3 is the biggest, so it will be the largest speed. Most probable, which had root 2 RT by pi, 2 RT by m, that will be the smallest speed, and root 8 by pi. 8 by pi is more than 2 but less than 3. It will be in between of them. That's how the order goes. So that's what I have marked it right over here in the Boltzmann distribution, the distribution of the molecules versus the speed. That's how it looks like. If that is clear, give me a thumbs up, and if you're enjoying it, also go smash the like button down there in case you have forgotten to do so. Are you guys clear? Very good, Selva. Yes, root mean square is the biggest, and let's get moving to the first question on these concepts. At what temperature is the root mean square velocity of gaseous hydrogen molecules equal to that of oxygen molecules at 367 degrees Celsius? Okay, come on, let's see how to do this. The class might be up to 8:30, 8:45. Yep. And the good thing is now Shivan sir will not be taking classes at 9 o'clock. So I have that flexibility to push my classes to even till 9 o'clock. Yep. Very good, Aishwarya. Let's move on. What temperature is the root mean square velocity of the gaseous hydrogen molecule equal to that of the oxygen molecule at 367 degree centigrade? Now 367 degree centigrade, first of all, convert it into Kelvin. So if you add plus 273, what are you going to get? Come on, look at this. You're going to get, yep, 640 Kelvin. Check this out. Are you going to get 640 Kelvin? Yep, very good. Now, all you need to do is just equate the velocities. The velocity of the hydrogen is equal to velocity of the oxygen molecules. So velocity of the hydrogen molecules will be, okay, so I do not know the temperature, and remember one thing, it's the root mean square, so I should have 3RT. I don't know the temperature. M, what is the molecular weight for hydrogen? It will be 2, right? So I'm just going to put 2 over here. I hope this makes sense to all of you. And on the other side, for oxygen, I'm going to put RMS, that means 3R temperature. Temperature is 640 divided by M, molecular weight for oxygen, that will be 32. So put 32. Root goes, 3R goes. So I'm just left with T by 2 is equal to 640 divided by 32. Now 2 and 32 goes 16 times, and 16 over here will go 40 times. So that means the answer should be 40 Kelvin. Yep. Very good, Gauri, very good. Chandana vlogs. No, Shri, it is not A, it is 40 Kelvin. Okay, that's how simple this question is. So 3 RT by M, 3R, root just goes away. It was only a gimmick of temperature and molecular weight. So anyways, you know, the root goes off, the temperature, you don't even have to find the roots of anything. So it becomes a very easy calculation. Moving on to the next one. Yes, option C is correct. There are two vessels, each having equal volume containing molecular hydrogen at 1 atmosphere and helium at 2 atms. Atmospheres means atm, atmospheric pressure. If both are at the same temperature, then the mean velocity of hydrogen molecule is equal, twice, half, root 2 times that of helium. Very interesting question. Let's see how many of you can get this. Yes, gadbad should not be done. Very good, true. Okay, so let's see. Come on, my warriors, figure this out. Let's see if you can get this. Oh, looks like you guys were having some fun. I don't know what was going on. Some kind of chats was going on. EGL and somebody. I don't know what was happening. Yes, EGL. Of course, I remember you, man. How can I forget you? I won't forget you, EGL. Yes. And what you need to do over here is that, see, the temperature is same, but one of them has hydrogen, and the other one has helium. The pressure could be different, but remember, the velocity is nothing but always some constant will be there. Temperature will be there, M will be there. Correct? So all that matters is temperature and M, but out of that the temperature is same. Very interesting thing, the temperature is same. That means only M is different. So if I talk about velocity of hydrogen upon velocity of helium, it will be nothing but molecular weight of hydrogen will come below and molecular weight of helium will come on the top. And molecular weight of helium will be 4 and for hydrogen it will be 2. So it will be basically root 2. So velocity of hydrogen will be root 2 times velocity of helium. So I think it is there over here. It is root 2 times of helium. So that's the velocity of the hydrogen molecule. So option D is correct. Got it, my warriors? Very good. Excelente, excelente. So it's just based on the concept of velocity being proportional to some root of temperature. Constant doesn't matter. Molecular weight comes below. M is different. That's why the speeds are different. Keep this in mind. A lot of people think if temperature of two gases are same, their speeds will be same. That's completely wrong. If the temperatures are same, speeds may or may not be same because M, molecular weight, could be different. So this is a very good question which tells you about that. Now, here is another interesting question. Remember back in momentum and collisions, whenever a ball, whenever some object collides with a wall and rebounds back, it imparts some impulse, correct? Look at these molecules. Don't you get the same feeling? These molecules are colliding randomly with all the walls of the container. Aren't they imparting impulses? Aren't they imparting impulses? So, think about it. If the molecules are imparting, they are imparting impulse, okay? If they are imparting impulse on the walls, that impulses which are acting, if I average it out per unit time, per unit area, think about it, impulse per unit time will give me force. And if I divide that with area, so force divided by area, that's going to give me pressure. That's going to give me pressure. So basically, if you calculate the amount of impulse per unit time for all the molecules per unit time, per unit area, that is going to give the pressure of the gas, which is being exerted on the walls of the container. Yes, and that turns out to be P is equal to 1/3 small m capital N by volume V RMS square. A better way of writing, usually, this is how you usually write it. PV is equal to 1/3 small m capital M V RMS square. This is a very, very crucial and important equation which completely is dependent on the fact that the molecules impart impulse and that per unit time creates force, and that force on that area gives you pressure. So it's just based on this fact. Here again the small m is the mass of a molecule. It's the mass of a molecule. That means it is capital M by Na, and this N stands for the number of molecules. Is the number of molecules. So remember, N is number of moles into Avogadro number. So this N stands for your moles, okay, and this Na stands for 6 into 10 to the power 23. This is what it is. And VRMS, of course, we just figured this out. That was nothing but 3RT by M. So that was your VRMS. Now the best part is, this is your home assignment. If you just substitute this equation here and this over here and this over here, guess what? When you solve this, what are you going to get? Just substitute this in your rough work and see what you guys get. Just substitute it. Just substitute it. What are you going to get? Just try it out. in your rougher, and let me know in the chat box what you exactly get when you substitute all of these things. You're going to get one very fascinating thing. You're going to get a very fascinating thing. Just play around with this. Guess what? If you solve this, you are just going to get, yep, guess what? If you substitute all of this, you're just going to get PV is equal to nRT, nothing else. You're just going to get PV is equal to nRT, nothing else. Yep. So basically, it just, if you do the reverse calculation from gases law, you are going to get this equation, and if you substitute these values, you get the ideal gas equation. So either you know this or you know that, you can derive the other one. Yes, it's the ideal gas equation. So basically, ideal gas equation is being derived experimentally. So from this, you can arrive at this, and you can also from this come to the RMS velocity. That's what I wanted to tell you. Okay, let's start solving some questions. Yep, isn't it interesting? So these are different ways of seeing the same equation. PV is equal to 1/3 mnV RMS square. All right, in the ideal gas at temperature T, the average force that a molecule applies, on the walls of a container depends on temperature as T raised to something. What do you think the value of that power of T is? Yep, EGL, I doubt there might be some eligibility criteria. I think they are going to waive off that eligibility criteria. So don't worry about it, okay? So let's see what are we going to do over here. All right, so there we go. First of all, a good estimate for this value, and it applies some force. This is the average force. Now what is the average force exerted going to be? It is going to be the pressure. It's going to be the pressure multiplied by the area, right? It's going to be the pressure multiplied by area, because pressure is force by area. Now what is the pressure? I just told you PV is equal to 1/3 nmV RMS square. So I can write pressure as 1/3 nm, okay, VRMS square, the whole thing divided by volume. This is volume, that is speed. Don't confuse the two. Into obviously the area. Now N, leave it out. M is a constant. This is volume, okay. Volume is also taken out. Area also just take it out. Just write it in a different form. N M A divided by volume. RMS velocity. RMS velocity was nothing but 3RT by M. All right, and take the root and square it. The root goes off. So VRMS square will be 3RT by M. So now if you notice, this average force, isn't it proportional to temperature? Because all the other things are just constants. Isn't it just proportional to temperature? So what is the power of T? The power of T is 1. Hence the answer C should be correct. Yep, it is option C. Perfecto, my warriors. Excelente. Very good. That's the answer. Moving on. Degrees of freedom. Here is the thing. Sir, density form of an ideal gas equation. Ramya, the density form of an ideal gas equation, if you want it, I'll just give it to you over here only, where I had given you ideal gas equation. So the density form, okay, let me just put it in the notes so that it is there for all of you. So the density form will be over here. I'll just put it. Pm is equal to rho RT. M is the molecular weight. This is your density. This is your density. Very, very important. So this is another way of remembering the ideal gas equation. Pm is equal to rho RT. All right, that's all. Okay, moving ahead to the next one. Where are we? Yes, let's go ahead. Yes, this was all done. Done. All right, this was also done. Okay, degrees of freedom. Now, many students get confused when we talk about degrees of freedom, and they make us some, very peculiar mistakes, and I want you to avoid those mistakes. See, every molecule has certain amount of energy. Now, let's say I take a molecule somewhat like this. Okay, let's say I take a molecule over here. This is a molecule of helium. It can travel this way. It can also travel like this in the z-axis, x-axis. It can also travel along the y-axis. So it can have translational kinetic energy. It can have translational kinetic energy in the x, in the y, and in the z axis. This is your helium molecule. Similarly, as the molecule is translating, it can also spin. It can spin like this. It can also spin like this. It can also spin like this. This is your rotational kinetic energy. Now, if I tell you what is the total energy, of that helium or whatever that monoatomic or whatever that molecule is, you will be like, it is the sum of all kinetic energies. So it is basically translational kinetic energy in x, y, z plus the rotational kinetic energy, which is basically the spin kinetic energy in x-axis, y-axis and z-axis. X-axis, y-axis and z-axis. Now think about, now this is very, very important, very, very important. Remember that when the helium molecule rotates, it's a point. When it spins, what do you think the moment of inertia will be? Won't it be negligible? If you take a point mass, a small spherical mass, if it spins about itself half or whatever, 2 by 5 mr square, 2 by 3 mr square, whatever you write, won't it be very small? So won't the rotational kinetic energy be negligible? Won't the rotational kinetic energy be negligible, my warriors? Think about it. So this part is negligible. You are just going to neglect it. It's not of any significance. Only half mv square, half mv square, half mv square, that is going to be significant. That's the reason why we say that the degrees of freedom for helium, which is monoatomic molecule, is 3 in number, because it has 3 translational kinetic energies which are significant. It's not that it can't rotate. It will rotate, but it's of no use when you count the energies. So whenever we talk about degrees of freedom, it's not just about the independent ways it can move, but it is also the ones which are significant, which can account for the kinetic energies. So the ones which do not contribute in the kinetic energies, you're going to forget about it. Got it? Is this entering your head, my warriors? Similarly, let's see if we can understand this. Imagine you have a hydrogen molecule. Hydrogen molecule is a diatomic molecule. Hydrogen molecule is a diatomic molecule. Oh yes, thank you, Ijal. My hair is like a nest actually. Yes, there were 2 pigeons which built their nest when I was out of Bangalore behind the cupboard. So when I came, in fact, I'm not kidding, actually there was a nest. And they built, they had so many twigs and leaves behind our cupboard, so I had to shoot them away. Then the pigeons negotiated with me. They're like, you want to get rid of us, you need to provide us shelter. So I was like, okay, fine, I'm going to grow my hair, you can lay the eggs in my hair. And but yeah, the deal is, once the birds hatch, you need to take away the nest out of my hair and I can cut my hair. So they agreed, and that's how the deal was made, and I got my a cupboard also cleaned. So it was a fair deal, I suppose. So if you hear some chirping noise, just ignore, okay? So those are the birds just playing around, so just let them be. It's a deal, okay, for a few days. All right, so here we have hydrogen. That hydrogen molecules, they can travel in the x direction, they can travel in the y direction, they can also travel in the z direction. So it has 3 translational kinetic energies. 3 translational kinetic energies. Let's talk about the spin. Let's talk about the spin. Number 1, it can spin like this. The 2 molecules are here, they can spin like this. It has good moment of inertia. You'll be like, sir, it is rotating, you should ignore it. No, I'm not going to ignore. look at the points. The points are at some distance. It's like holding two dumbbells. And when it rotates, won't it have some significant moment of inertia? Remember, moment of inertia depends on the distance from the axis. The more the separation, more is the moment of inertia. So yes, they will have moment of inertia. In fact, even if you rotate it about the z-axis, it will have moment of inertia, and that energy should be counted when the molecules rotate like this. But you know what should not be counted is this one. This should not be counted, because when it spins like this, it's like the 2 points are spinning about the axis. It's one axis, the molecules are spinning like that. So that will be not counted. So hence, what is happening is we are going to have only 2 rotational kinetic energy degrees of freedom. Yep. I hope this is clear. I hope this is clear. Understood, my warriors? Yep, very good. So totally it has 5 degrees of freedom. Now, similarly, you can think of a triatomic molecule like CO2. This is a CO2 molecule. A CO2 molecule is linear. When a CO2 molecule is linear, can you guess the number of degrees of freedom, my warriors? Think about it. Translation, 1, 2, 3. 3 translation. So 3 translations done. Rotation wise, 1 and then 2. But it can't spin like this. It will be of no use. So 2 rotational degrees of freedom. 2 rotational degrees of freedom. That's it. Gone. So a linear triatomic molecule will have 5 degrees of freedom. 5 degrees of freedom. No, it will not have 6. It will have 5 degrees of freedom. Similarly, if you have some other molecule like H2O, okay, so if you have molecules like H2O, which is non-linear, this is non-linear molecule, then when you have molecule here, atoms here, here and here, apart from 3 translation, the 3 rotation will also be there. For non-linear, why will I have 3 rotations? Because they are not in a straight line. So when I rotate, imagine a molecule at an angle like this. Imagine a molecule at an angle like this. I can spin it like this. The rotation will be significant. I can rotate it like this. It will be significant. So along Y I can rotate. I can also rotate it like that. Along Z, I can also rotate it along X. So all the rotations are significant. Hence 3 rotational degrees. Hence 6 degrees of freedom. Understood? So that's how degrees of freedom are calculated. Okay? And I have shown it to you in these simple diagrams. Of course, there could be more degrees of freedom. And yes, I am coming to that, Aryan. What is vibrational degrees of freedom? So you understood translation, you understood rotational. Sometimes at extremely high temperatures, the molecules can alternatively go back and forth like simple harmonic motion. So they can, vibrate like this. So they can develop additional degree of freedom, but that becomes significant only at very high temperatures. So for normal temperatures, that vibrational degree should not be counted. Yep. So Anirudh, that's what I'm giving you the example. At very, very high temperature, okay, 2000 Kelvin, 3000 Kelvin, that's when the molecules, apart from translating means both the molecules go together. Both of them go like this, both of them go like this, both of them go like this. That is translation. Spin is both of them go like this together. Vibration is both of them don't go together, they will vibrate, they will have relative motion. That is that extra energy which you need to account for. That's why that extra degree comes only at very, very high temperatures. Is that now understood, my warriors? Yep. I hope this is clear. Very, very important. For normal temperatures, it will not come. So vibrational will also come at very, very high temperatures. Very good. Okay. So vibration is relative motion between the molecules. Okay. Now we have a law for all of this. We have a law for all of this. It says a molecule can rotate, translate, vibrate, and each of them can be in different amounts, 3 degrees, 2 degrees, whatever. But the energy is distributed equally among all of them. There is no reason why a particular form of energy should be more than the other form. The energy gets distributed. Oh, you also take this, x-axis, okay, you take this energy, y-axis, you take this energy. All the energies are divided equally among everyone. That's the law of equipartition of energy, and it basically says that each degree of freedom has half kT energy per molecule per mole. Very, very important. I'll just put it over here. Each degree of freedom has energy of half kT per molecule. Very, very important. Per molecule. Okay, that's very, very important. This K is your Boltzmann number, which is R divided by Na. Now, I'll just give you an example. Imagine if I talk about, let's say helium molecule. So for helium molecule, how many degrees of freedom are there? The degrees of freedom are translation 1, 2, 3. Rotation, nothing. So 3 degrees of freedom. This is monoatomic. So the total energy of the helium molecule will be, each degree has half kT. 3 degrees. So 3 times of half kT. 3 times of half kT. As simple as that. Similarly, if I had, let's say, oxygen molecule. Oxygen molecule has degrees of freedom 5. So the total energy, how much will be the total energy? It will be 5 into half kT. 5 by 2 kT. As simple as that. This is what you get. This is per molecule. Very, very important. Per molecule. So, if they ask you what is the total energy of the gas, so you multiply it by the number of molecules, you will get the total energy, of the gas, nothing else. Because this is per molecule, so number of molecules you multiply, you will get it for the entire gas. As simple as that. Okay, this is how it works. So half kT is the energy which is distributed per molecule per degree of freedom. Now let's talk about the internal energy. Very, very important, my warriors. Excellent, Anirudh, Shripriya. I can see all of you answering out there. So say for example, I talk about, okay, what is this internal energy? First of all, internal energy is nothing but the sum of kinetic energies plus the sum of potential energies. Very important. But recollect our assumptions right at the beginning. Didn't I tell you that the molecular forces are negligible? If the molecular forces are negligible, will they have potential energy associated with it? Yes or no? Think about it. Will they have potential energy? Because potential energy comes only when there is a force of interaction. If there is no force of interaction, the molecules don't exert repulsion or attraction, the force will be zero, potential energy will be negligible. So this is zero and this is zero because no intermolecular forces. No intermolecular forces. Very, very important. So the only energy, internal energy which is there, it is only basically the sum of kinetic energy, and this is true for an ideal gas. Very, very important. So the internal energy is only the kinetic energy for an ideal gas because potential energy is not there at all. Now, if you try to calculate this, how much is that internal energy? It's very simple. I'll show that to you. U will be, for a gas, will be number of molecules, okay, number of molecules multiplied by energy per molecule. Very, very interesting. Number of molecules into energy per molecule will give me the total energy of the gas. The number of molecules is capital N. Energy per molecule is degrees of freedom into half kT. Everybody remembers this? Half kT is per degree into F will give me nothing but the energy per molecule. Into N is the total energy. Let's see what do we get next. F is as it is, and this K I can write it as R divided by Na into T. Now let's rearrange this. Okay, so what I'm going to do, take this n over here. So I'm just going to get, okay, n by Na into F into R divided by 2 into T. What is n by Na? Number of molecules upon Avogadro's number. That's going to give you the number of moles of that gas, isn't it? So won't this be n F R by 2 into T? N F R by 2 into T. Now this is very interesting. What is R F by 2? Do you know what is this? Yes, else gallery, you will see the notes as well in the Telegram channel. What is this FR by 2? This is the CV of the gas, specific heat capacity. You're going to learn about it in a bit. But yes, this is nothing but NCVT. So the internal energy of a gas is nothing but N into CV into T. Yep, N into CV into T. No, it was not M, it was small m. Number of moles is number of molecules by Avogadro number. So that's the number of moles, correct? Yep, very good. So NCVT. So that also means the change in internal energy. What will be the change in internal energy? It will be NCV delta T. This is how this equation comes. So energy of a gas is just NCV into T, but the change is NCV delta T. This is how the expression comes. Yep. U is a state function. Yes, Dakshin, because it only depends on the temperature change. It does not depend on the process. It just depends on the initial and the final state. Yes, so that's why it is also a state function. It does not depend on the path of the process itself. So it is also probably overlapping out here. Probably I will delete this part while I give you the notes. So don't worry about it. I'll just delete this part later on while sharing the PDF with you. All right, don't worry. All right, great. Moving on to the question coming up on your screen. What do you think is the ratio between translational energy of 1 mole of oxygen and rotational energy of 2 moles of nitrogen at 300 Kelvin? Yep. Is CV specific heat capacity at constant volume? Yes, Nandini. Yep, it is. I'm just going to come to that CV part in a bit. Just give me a moment. I'm going to come to CV as well. Okay. Sir, in 12th, one comment out how to solve the values which is in powers with multiple decimal values. Varsoi. It's just practice and making sure you know the tables at least till 30, knowing the squares, and also making certain approximations and also eliminating the options. That's all. All right, cool. So let's see how many of you can solve this question. What do you think is the ratio between the kinetic energy of 1 mole of oxygen and rotational kinetic energy of 2 moles of nitrogen? Let's try and do this question first. All right, so ratio of the translational kinetic energy, I believe, translational kinetic energy. Okay, so this is translational for, you know, oxygen upon the kinetic energy of rotation, but that's for nitrogen, so that's N2. Let's see, what do we do? How do you find the kinetic energy? The kinetic energy is nothing but the internal energy. I just told you this, right? The internal energy of a gas, the internal energy is nothing but the kinetic energy, because the potential energy is a big fat 0. So you just take the ratio of the potential energy, ratio of the internal energy, and U is nothing but, I just gave you the formula, it was NCV into T. NCV into T. That's all. And remember, the CV was nothing but FR by 2. It was nothing but RF by 2. So just start substituting this and let's see what do we exactly get. So for oxygen, how many moles are there? 1 mole. So 1 mole. So that means 1 into CV. For oxygen, how many degrees of freedom are there? It's a diatomic. So 5. So this will be nothing but 5R by 2. Is that making sense, my warriors? Everybody clear about this? Great. Into temperature. What is the temperature? It is same, 300 Kelvin. Fair enough. Now, how many? Oh, but only we have to take into account translation. So, do you write the degrees of freedom as 5 or something else. That's the catch. Because of this word translation. Because of this word translation, you cannot write 5 over here. Think about it. Because it is a diatomic molecule, there will be only 3 degrees of freedom. 3 degrees of freedom. So I'll just put 3 over here. Does that make sense? Very good. Similarly, when you write kinetic energy for nitrogen, number of moles is 2. So 2 will come as it is N. F, diatomic. One will be like this kind of a degree of freedom, other will be like that. The other third degree of freedom for rotation will not come. So it only has 2 rotational degrees of freedom. So 2R by 2 into 300 again. You can see so many numbers get cancelled. 300, 300, 2, R gets cancelled. I'm just left with 3 divided by 2 into 2, which is 3 divided by 4. Is it there somewhere? Yes, it is. Yes, it is. Option C, my warriors. Perfecto. Perfecto. Option C is correct. So this is a brilliant question. Many students miss the fact that translation and rotational is asked. Number 2, they forget the moles. Also, they get confused between the formulas. So that's how you need to solve it. Got it, my warriors? Perfecto. Let's move on to another question. This is very interesting. Many students are going to make some silly mistake. Here, V, VRMS, VP. V is average, VRMS is RMS, VP is the most probable speed, okay, of the molecules. And it's a monoatomic gas at temperature T. The mass of the molecule is M. Only one statement is correct. Let's see how many of you can get this. No molecule can have a speed more than √2 RMS. No molecule can have a speed less than √2, 1 by √2 times VP. The average speed is less than most probable speed, is less than RMS speed. And the average kinetic energy of the molecule is 3 by 4 mVp square. Interesting question. Let's see how many of you can solve this question. Very, very interesting. Guys, I think you can solve this question even by elimination. Think how? Don't you remember the Boltzmann distribution, speed distribution curve? I had just given it to you. Look at this. I had just given it to you. I'll just go back over here. Okay, there we go. There are all kinds of speeds. Yes, there are very few molecules with very little and very large speeds, but there are. That option said there is no such molecule. That is obviously wrong. You have all kinds of speeds available, right from 0 till very large values. Number 1. Number 2, RMS is larger than average. Average is larger than most probable. If you go back to that particular slide, you will notice over here, RMS is here, probable is in between, average is here. This is wrong. Obviously, this option is wrong, my warriors. Do you see that? This is wrong. What should be the correct order? The correct order should be most probable is least, then you have the average, and then you have the RMS, right? This was the correct order. So this is wrong, this is wrong, this is wrong. Obviously, D option will be correct. Yes, D option will be correct. Now, if you are wondering, how can we prove it? Is the average kinetic energy of the molecule 3 by 4 m Vp square? Yes, you can get that easily as well. See, it's a monoatomic molecule. It's mentioned over here. It's a monoatomic gas, right? So, for the kinetic energy of that monoatomic gas, remember there are 3 degrees of freedom. So, 3 into basically, you just have to use NCVT. Just use NCVT. I think you will get the answer and you can just rearrange it. But anyways, let's just try this out. So, this will be 3 into, these are the degrees of freedom, half into K into T. This is the energy of a molecule, but there are many molecules like that, and number of molecules is N. So just put N over there. Is the number of moles mentioned? No, it's not mentioned. So now just need to solve this right over here. So this will become 3 by 2. K you can write it as R by NA, and then T will come over here and N will also come over here. Now I don't want this T. I'll get rid of this T in a very simple manner. What I will do is recollect most probable speed. most probable speed was root of 2RT by m. So basically from here, temperature, square both sides and rearrange. Square, you will get temperature is Vp square into m divided by 2R. Vp square m divided by 2R. 2R will come below, m will go on the top. Okay. So just put, instead of temperature, you put Vp square into m divided by 2R, and the rest of the terms will come as it is. So this will be 3 divided by 2. This will be R divided by Na, and you will also have n. Now check this out. R will get cancelled. Yes, R will get cancelled. This is needed for the entire gas, for the molecule. It is per molecule, so I need not multiply it by n. So I don't have to multiply it by n. It was per molecule, so I don't actually need that n. So I can just get rid of this. So if I don't want it for the entire gas, so if it was per molecule, I don't need that n at all. So m by Na, this 2 into 2 will become 4. So m by Na will be nothing but the mass of a molecule, and this will become Vp square, because m by Na is mass of a molecule, and we were asked over here the energy of the molecules. So per molecule, what is the average energy? That's it. Yes. So why we use most probable speed here? Yep. The reason is, Dakshin, in the fourth option, do you see Vp? Vp stands for most probable speed. That's why we used Vp, just to prove the fourth option correct. Otherwise, I didn't even have to do it. I eliminated options A, B, C by logic and the previous theory. So obviously D was correct, but just to satisfy you, I have made sure that I solve the last option. Yep. So m by Na will be the small m. Yes, Shripriya. I hope this is clear. I hope this is clear. Yep. Understood, clear, my warriors? Let's move ahead to the next question coming up on your screen. Okay. Yes. Before that, I think we need to figure out the relationship. So number of moles is equal to mass by molecular mass. Rearrange. No. In the previous thing, remember this n was not needed, because here it was asked of the molecules. So m, molecular weight divided by Avogadro number, will actually give me small m. This n was not even needed. Okay. So what was asked was without that n, per molecule it was asked. Okay, Bharni, that was fine. That was correct. All right. Cp and Cv, very straightforward relationship. The ratio and the difference. Well, first, what is Cv? Cv is specific heat capacity, but when the volume is constant. Remember, I had mentioned about this in calorimetry chapter. Remember that, when you have a gas and when you heat it, you have multiple ways of heating it. You can keep the volume constant and heat it, or you can keep the pressure constant and heat it. And the specific heat capacity depends on how you are heating it. When you heat it at constant volume, you are placing it in a rigid container, then it turns out to be Cv. Cv is the specific heat capacity at constant volume. When you heat it at constant pressure, pressure is constant, you can allow it to expand or contract, then it is Cp. Cp is the specific heat capacity at constant pressure. Now, the relationship between them is given by the Mayer's relationship, and also the ratio is called as gamma, Cp by Cv. I'll just put it up right over here so that you know what it is. Okay. See, this gamma which is there, gamma is called as the ratio of Cp by Cv, and remember, Cp is always more than Cv. In fact, the difference of the two is called as the Mayer's relationship. Cp minus Cv is equal to R. This is only true for an ideal gas only. This is only true for an ideal gas. This is called as the Mayer's relationship. Okay, Mayer's relationship. How do you get this relation? This comes via the first law of thermodynamics. By the first law of thermodynamics, you get Cp minus Cv is equal to R. Now, this gamma is nothing but Cp by Cv. Now, Cp and Cv, you can find it out using these relationships. I'll tell you how. I just told you Cv is Fr divided by 2, correct? Fr divided by 2. That means Cp will be Cv plus R, which is Fr by 2 plus R, which means it is F by 2 plus 1 into R. That's what Cp is going to be. Now when you take this and substitute it over here, what are you going to get? You are going to get F by 2 plus 1 into R divided by F into R divided by 2. That's what you are going to get. Yep. So what is the final answer that you are going to get out here? So I'll just erase this because it was already there. I'm just going to erase this. Okay. I'm just going to get it up on the screen. Okay. So what are you going to get eventually? You are eventually going to get this. Cp by Cv will be F by 2 plus 1 into R, F by 2 R, RR goes, rearrange it, you are just going to get 1 plus 2 by F. That's what you're going to get. Very interesting. Okay. So this is the final relation. This is degrees of freedom. This is gamma. Very, very important. Very, very important. You should know this by heart. Gamma is 1 plus 2 by F. Keep this in your mind. You cannot afford to forget this. Yep, gamma is 1 plus 2 by F, gamma is Cp by Cv, Cp minus Cv is R. The difference of that is R. Alright, that's all. So this is how you relate specific heat capacity at constant pressure and specific heat capacity at constant volume via Mayer's relationship, and the ratio is gamma. That's the specific heat ratio for the gases. Let's see whether you can solve this question. A diatomic gas molecule has translational, rotational and vibrational degree of freedoms. Cp by Cv ratio is going to be how much? The question is, what is the ratio of Cp by Cv? Come on, figure this out. It has translational, it has rotational and it has vibrational degrees of freedom. The question is, what do you think is the ratio of Cp by Cv? If the ratio of Cp by Cv is asked, basically they have asked gamma. And gamma is 1 plus 2 by F. So how many degrees of freedom does it have? Translation. So translational wise, obviously it will have 3 translationals, one in X, one in Y, one in Z, 3 translational degrees of freedom. It's a diatomic molecule, so rotation wise it will have 2 degrees of freedom, one this way and one other way. So for a diatomic molecule, 2 degrees of freedom will be there. Thus rotation about the axis should be ignored. Next, vibration. So when I talk about vibration, the molecules go back and forward, so there will be 1 degree of freedom because of vibration. So if you count this, it will become 1 plus 2 by the total degrees of freedom is nothing but 6. So this will become 6. So 1 plus 1 by 3, which is nothing but 4 by 3. And 4 by 3, that's 1.33 my warriors. That's option D, correct? Yep. No, it's not 1.67, be careful, it is 1.33. Yes, in Mayer's relationship, R is the same gas constant. Remember during ideal gas equation, I told you that R, that is that same R, that same gas constant. Yep, it is, Ramya, it is. Okay, the same gas constant. It comes via the first law of thermodynamics. Very interesting, very important question because it had vibrational degrees of freedom. Many students make a mistake and put it up as 1.67 or something else. Be careful. In an ideal gas A and real gas B, their volumes are changed from V to 2V in isothermal condition. Very important. The increase in the internal energy is how much? How to know vibrational? Dakshin, it will be given to you in the question. So if it is given that it is very high temperature or it has vibration, you take into account 1 vibrational degree of freedom. That's all you need to do, Dakshin. Okay, bacha, let's see if you can solve this question. Here there are 2 gases. One is an ideal gas, A. So for A, which is ideal, U or rather delta U was NCV delta T. Because it is clearly mentioned isothermal, that means delta T will be 0. So delta U for A gas will be 0. Makes sense? Temperature is constant, so change in internal energy will be 0. But for the second gas, that's a real gas, So for B, delta U is change in kinetic plus change in potential energy. Kinetic energy change will be 0. Kinetic energy change will be 0. But for a real gas, potential energies, the distances, molecular forces will be there. Delta P will not be 0. It will not be 0. So hence delta UB for the second case, when you have a real gas, it of B will be more than that of A. A's change will be 0. B will have something 0 plus something over here. That's something over here because of intermolecular forces. So hence for B, you will see the change in the internal energy will be more. Many students make a mistake and say it will be same because it is isothermal. Wrong. This is real, this is ideal. So you need to take that into account. Yeah. So there is one last theory left, Ankit, and then this is the last theory left, and then we'll have the last 1 or 2 problems. Beautiful question on mixing of gases. See, we have in this chapter till now calculated the speeds, specific heats for constant volume, for constant pressure, the ratio of Cp and Cv, which is called gamma, all of that. But what when the gases mix together? If hydrogen is mixed with nitrogen, nitrogen is mixed with oxygen, then I want to study them together. You can find their equivalent specific heat for constant volume, for constant pressure, and then you can also find their equivalent gamma and all those things. So whenever gases are mixed, remember you need to find their equivalent specific heat and all of that. So all you need to do is this. Remember, gas 1 mixed with gas 2, N1 is the moles of gas 1, N2 is the moles of gas 2. Remember one simple fact. This is the mixed quantity. Let's say this is CV1. Let's say this gas had CV2. The mixture had specific heat capacity CV. Okay, that CV is the mixture specific heat capacity. The total moles here, the reds and the blues add up, will be N1 plus N2. These are the total moles in the mixture. Total mixture moles, correct? Now think about it. When you add them, how are you going to find the specific heat capacity at constant volume for that mixture? All you need to do is use this fact that the change in internal energy of the first gas plus the change in internal energy of the second gas will be the change in internal energy of that mixture. Now for the first gas, it will be N1 CV1 delta T. For the second gas, it will be N2 CV2 delta T. For the mixture, it will be N1 plus N2 CV into delta T. Delta T, delta T, delta T goes. You will have N1 CV1 is plus N2 CV2 is equal to N1 plus N2 into CV. From this, you will get CV is equal to N1 CV1 plus N2 CV2 divided by N1 plus N2. That's what you will get, CV. Similar logic if you use, you will get Cp is equal to N1 Cp1 plus N2 Cp2 divided by N1 plus N2. This is the Cp of the mixture. And lastly, if you take the ratio of the two, you will get gamma of the mixture. Lot of students make this mistake and they write gamma of the mixture is N1 gamma 1 plus N2 gamma 2 upon N1 plus N2. This is not correct. Please keep this in mind. This is not correct. This is wrong. In fact, the gamma of the mixture is Cp of the mixture by Cv of the mixture. Now if you divide this with this, N1 plus N2, N1 plus N2 will cancel and you will have N1 Cp1 plus N2 Cp2 divided by N1 Cv1 plus N2 Cv2, which is completely different from this. Which is completely different from this. I hope this is clear. Okay, so Vignesh, I think you should watch this lecture because this is more in detail. This was the other one was last year. Yes, you can gain some insights from the last year's lecture as well, but this year I have put in even more effort, even more different problems, so you should watch this class. All right, I hope this is understood. By the way, I had also put it behind the background, but if you want me to leave this in the notes, I think I'll leave this in the notes, but I think I should remove the background behind. All right, I'll do that later on. Okay, are you ready for the last two questions? Okay, are you ready for the last two questions, my warriors? Let's do this. 2 mole of oxygen is mixed with 8 moles of helium. The effective specific heat of the mixture at constant volume, CV of the mixture. That's what they have asked, CV of the mixture. Let's try and do this question. So CV of that mixture will be N1 CV1 plus N2 CV2 divided by N1 plus N2. Number of moles of oxygen, that is 2. CV for oxygen, what will be the CV? It's a diatomic. So how many degrees of freedom? 5. So 5 FR by 2, 5R by 2. So this will be 5R by 2 plus N2. Number of moles of helium, that's 8. So 8. Helium is a monoatomic. Mono means 3 degrees of freedom. So CV will be 3R by 2. So whatever degrees of freedom into R by 2. Okay. Divided by N1 plus N2. So 2 plus 8. So what are you going to get? 2 cancel. So you will just get 5R. And 8 and 2 cancel. So 4 3s are 12. 12R divided by 8 plus 2, that is 10. So 5 plus 12, that's 17. 17 by 10 is 1.7R. So that should be option C, I believe. Yep, that's true. Very true. 1.7R. That's correct. Yeah, that's the answer. Interesting. Moving on to the next question coming up on your screen. A gas mixture contains 2 moles of oxygen, 4 moles of neon at some temperature T. Neglecting all vibrational modes, the total internal energy of the complete system. They have asked you the internal energy of the complete system. So think about it. How are you going to calculate the total internal energy? So the internal energy of the system will be internal energy of oxygen plus internal energy of neon. Both gases are mixed. So energy of neon, energy of oxygen, if you add it, you will get the entire energy of the mixture. What's the energy of oxygen? For oxygen, I think I'm going to use number of moles of oxygen into CV of oxygen into temperature plus number of moles of neon into CV of neon into temperature. Let's write it one by one. Number of moles for oxygen, that's 2. Oxygen is diatomic, so 5 degrees of freedom. So CV will be 5R divided by 2 into T plus number of moles of neon, that's 4. Neon is inert gas, so that means 3 degrees of freedom. So CV will be 3R divided by 2 into temperature. Okay, 2 cancels, so I will get 5RT over here plus 4 cancels, so 2 3s are 6, so 6RT right over here. 5 plus 6 is 11RT. Is it there somewhere? Yes, it is. Option B is correct. That's the answer. Perfecto. Yes, this is Kinetic Theory of Gases lesson, Vaishal FF. Yep. Oh, okay, Anirudh. Fine. I'll give you some more time maybe next time. Definitely. Yes. So this is what it is, 11RT. Now, I'll be posting the PDF in our Telegram channel. If you are a part of the Telegram channel, good. If you are a part of the old Telegram channel, shift to the new channel. That's very important. Okay, even if you're watching this lecture recorded, put the answers for these questions in the comment section below. The answers with the solutions will be uploaded in the new Telegram channel only. So this is the first question. This is the second question on your screen. You can take a screenshot as well. This is your third question. Make sure you solve this as well. And this is, yes, your fourth question. So a lot of questions for practice. This is your daily assignment. After every class, if you keep solving it, you will get a lot of confidence. You will feel better about it. And especially for all the 11th standard students, let me tell you, we have the crash course running right now for all of you. That is basically for the 11th standard students to complete the portion in the remaining 2 months. And then you will be moving on to the long-term batch of 12th standard. So in the next 2 months, complete revision with test series, with modules, with assignments, everything that you need, and then move on to my batch in 12th standard, the long-term batch for JEE till you target JEE 2023. Yes, and where do you see that? Well, it's all there in the description box below. So when you're watching this video right over here in the description box, you can see the JEE 2-year course is right over here. So when you click on this, you will see entire 11th standard course with KVPY preparation, other micro courses, my micro courses, all other examinations including board examinations are targeted, everything. You don't have to join multiple classes, full 12th standard revision with CBSE revision, and you have 3 packages: Light, Classic, Plus. Light gives you everything what I told you. In Classic, you additionally get doubt solving on the mobile app after the class, and in Plus, you will get mentorship after the sessions are over, personal guide, personal tutor to help you out with your daily problems. So even if you try with the Light version, you can see the total cost till 2023, which is next year, whenever the exam will be, last exam, it's 54,000, and if you divide it by in the monthly installments, you will hardly get it for 3,000 rupees per month. You can even try it for 15 days for 1,350 rupees. Just click on this and you will see the coupon will be applied automatically, and you will save almost 10% of the total amount because of using the coupon code SHHPRO. Now best part is when you use the coupon code SHHPRO, you get additional 15 days. So it's not just 15, you get 15 plus 15, that's totally 1 month of a subscription. You can attend all the batches, as many as you want. You will get all the notes, you will get all the classes right over there. All right, so make the full use of it, and if you're happy, and then you can go and click on buy the complete course. So I'm really excited to see all of you very soon. When will the 12th portion start? It will start by March end or April 1st week. When will the portion for 12th nurture start? Around that time only, Vignesh. Okay, thank you Ankit, glad you enjoyed it. JEE 2022 Krishna Pranav, right now there are no updates, but I can see the downtrend. Remember I predicted this, I told you. In fact, I did not predict, I showed you the data, the official data. This was the graph, I showed you the graphs in the video. This is where the peak is going to be, and you can see cities like Mumbai and Delhi, their graphs have already started to plateau and become flat, and in the next few weeks I'm pretty sure it will come down, and that's when you are probably going to have the JEE announcement as well. Bye bye Roshni, take care. Yes, well, I don't remember you Amrita Varshini so much, but I remember hearing your name many times. All right, take care Shivali. Yes, COVID is going down Ankit, and everything will be good. Yes, Bharni, KTG done. So see you in the next class for 11th. That will be heat transfer. We'll do it in 2 classes, 1 lecture conduction, 1 lecture for radiation. That's how we'll complete heat transfer, and then we'll go to thermodynamics, the gas, the cyclic processes, heat engines, refrigeration, all of that in 2 lectures or so, and that's how we complete the thermodynamics part. Okay, we'll do it not very fast, but not very slow as well, because we have limited time. Bye bye, take care, have a great time Aishwarya, take care Dakshin, bye bye, all the best, hasta la vista. This was Captain Shreyas signing off.